So you are muted. So you are muted.
Okay, hello everyone. This is lecture 5 of Province Stats. So we would like to start probability from today. I hope you have done some practice on counting. As I said, computing probability is a lot about counting, especially the discrete one. But you will see that only 1/3 of the course, I would say, requires counting. The remaining we will do a lot of stuff. Okay, so let us start with the basic definition of probability. I know that you know these things from previous class, like higher school syllabus does have some probability, but let us quickly define probability and so on, right? So this is the content for today, is motivation for probability, and then we will define the classical probability. Okay, so what is probability? It's a measure that we use to measure how likely an event or outcome is. Okay, we will define what is an event or outcome. Okay, so in the simple term, for example, there is a 10% chance of rain. Okay, so these are like these are like measure. There's a probability that something it's 10% probability that it will rain today. So so as you can already see, it's about predicting uncertain thing, which looks like a paradox, but that's what probability theory is. Okay, so you are trying to with some measure you want to predict. Okay, of course, when prediction is involved, something may your prediction may be wrong. Okay, so this is what this subject is about. One of the question we can ask is like, how likely is that one player or team will win the game? Okay, so in the beginning you may not know if someone is playing a game, for example, in this case Ludo. Okay, you don't know. Okay, because there is a probability involved here, in the sense that the kid will throw a dice. Okay, and then if the kid is lucky, most of the time, maybe, okay, there will be some strategy involved here, but there is a lot depends on the chance. Okay, if the player is aware of the rules and so on. Okay, so so there can be many factors, right? So there is a chance, there is a strategy, and so on, but quite a lot also depends on the chance. Okay, so this is what we we will try to study in this course. Okay, and you will see that it's quite fascinating, and it has so many applications these days. You cannot live without probability now. Okay, whether it's yeah, you can do all kind of, especially with the new data science and so on. It's all a prediction game. Okay, so so the questions that we can ask usually is like, how likely is that one will win the lottery? Okay, so again, lottery is based on luck. Okay, so there are some uncertain things involved, and then it really depends on your luck, right? So how likely it is to rain or snow? Okay, so that's what I discussed before. Study of probability started with games of chance. Okay, so so when you see, games of chance are not really new things. These were played since long time. Like, people were always involved in some kind of game of chance. So the modern days are like roulette and so on. But people have been playing such games since a long time. Okay, if we can recall some of the epics, specifically centered on in India, is so-called Mahabharat. Okay, so that's a great war that happened about 900 BCE. Okay, so the proofs are up to 400 BCE, and it was a struggle between the two major group of cousins. Okay, you may ask, like, how come it becomes a big war, right? But these cousins had very big armies and so on, and some big warriors were involved, and that ended up killing to some estimate maybe millions and millions of people. It has everything: adventure, drama, suspense, thriller, you can ask for. And even a game of chance is involved in this, okay, in some sense. The intensity of the war, or the way things got intense, you can say, to some extent we can say that things are involved. A game of chance is also a culprit here. And in those days they used to play a game of chance which is called pasa, okay. It may have a different name, okay, and it is used also in other country, okay. So we don't know where actually it was invented, but so it may be, you can say that it's similar to the modern day Ludo, okay. So Ludo is the modern variant, but there are some differences and so on, okay. And then there are are the dice, but you can see the dice is like only four cornered, okay. It's not a I mean sides, okay. So it's not a six side dice, it's four sided dice, but there are two dice. So and um, so and there are yeah, so as I said, there are two dices, and then the move is determined by randomly throwing the two dices, right? Because if you throw and then you don't know which side will come up, okay. That's the uncertainty here. um, and the way the story goes is like, this game of chance was involved in Mahabharat, where some betting was done on Draupadi and so on, and things went out of control in some sense, and then that also had a contribution to the war. Okay, so if you want to know more detail, you can obviously look up. So this is these are the recorded history of game of chance. If you see from the Indian perspective, and obviously, as I said, it has been played by a variety of people around the game of chance have been very popular, okay, regardless of which type you think of. But these are the ways people used to entertain themselves. And in Europe, obviously, people were also interested in those things. And Cardino here in the picture, you can see Cardino is from Italy, and so this is the European context we can think of, early theory of probability. So here by theory I mean some systematic study of probability. Okay, the recorded history. Okay, we don't know if it was also done in some other parts of the civilization where some theory was built, but some solid recorded history can be found in Europe. And the one of the guys who was involved in the early development of probability theory was Cardino from Italy, and he was a very big gambler. Okay, so he used to gamble. He was gambling for about 25 years. So he did write few things. He analyzed few things. He came up with his own version of theory, and he wrote some notes on his experience with playing games. Okay, so in his famous 15-page page note, it's in Italian. Okay, Liber de Ludo Allier. Okay, I don't know what it means. Okay, actually, Liber is like is a game. Okay, so that's why it's a verb. Okay, so okay. Cardino's contribution, initial contribution, was so great that many actually considered him as a real father of probability. And this is what one of the biographer of Cardino, as you can remember, Cardino was also involved in one of the methods that you study in high school of solving the cubic equations, right? So if I remember, that is by Cardino. Cardino. Okay, I'm sorry, I'm pronouncing him incorrectly. Cardino. Okay, so one of the biographer, Austin Orr, wrote about him, and then he said that I have gained the conviction that this pioneer work on probability is so extensive and certain questions so successful that it would seem much more just to date the beginning of probability theory from Cardano's treatise rather than customary reckoning from Pascal's discussion. Okay, so what you can see from here is like what we see from the modern history. The people usually attribute the probability theory more to Pascal and Fermat, which is quite true. But as we will see from the historical findings that I will also show in this slide, is that Cardano actually came up with one of those major initial things, and then Pascal and Fermat later formalized a little bit more. Okay. Okay. So before I actually talk about a little bit more of the history, I would like to define few things because that will show up also in when we are talking about a little bit about history. A random experiment. What do we mean by random experiment? It's a process by which we observe something uncertain. Okay, so that's why it's random. Okay, so rain, up to our estimate, up to our knowledge so far, is an uncertain thing. Okay, we cannot really predict with very high precision that it will rain. So it's not a deterministic thing. It's not a certain thing. Okay, maybe in future if the science evolves and very nice. Nice weather models come that can take into account at very minute detail, then maybe you can predict to a large extent. But as we know from from our experience that real nature is quite random also at the atomic scale, especially if you think of stuff like quantum computing and so on. That's all probabilistic. Okay, so it's a very reasonable thing to assume that things remain very uncertain even at the atomic level. Okay, so if you happen to study quantum later on, then you will see that. Okay, so you need quantum probability theory there as well. Okay, so after experiment, we believe that after the experiment, at least the result is there. Okay, so that's what we expect. It's not just experiment, but let us say the experiment happened, and then after that I should have some result. If even the result is unknown, then okay, that's like that's like a useless experiment anyway, right? So what will you do with that? With even the results are not known, so no hope of building anything out of that. So an outcome is a result of a random experiment. Okay, so that's the outcome we are seeing. So when we are studying an experiment, we ensure that some outcome will be there at the end. Of course, that outcome is uncertain, but we need some outcome, and so that will be the result of the experiment that we are doing. Okay, so we toss a coin, and then the outcome is it will fall on some flat surface, and then the outcome is like either head or tail. Okay, either head or tail, that is what we are expecting. Okay, so the set of all possible outcomes will be defined as the sample space. Okay, so these are the key words that you should keep in mind. What is a sample space? Okay, so these are, you do a random experiment and the experiment does produce some results. Those are outcomes, and then you collect all possible outcomes you can think of. Here you may need counting. Okay, so you may need counting. So if I toss a coin, then the possible outcomes are head or tail. Okay, so that's the sample space for me. All possible outcomes are heads or tail. Okay, an event is a subset of the sample space. Okay, so the event. So basically, event is one of or a set of some outcomes from the sample space. Okay, sample space is a collection of all outcomes. For example, if you toss a coin, then the sample space is head and tail. Okay, it's that set. Okay, so sample space is a set containing head, comma tail. And event is one of those. Okay, so event is a subset. So let us say your event that you define is expecting a head. Okay, so then your event is a set containing head. Okay, so naturally event will be subset of the sample space. You cannot choose an event that is out of the sample space. That is not possible. Okay. Okay, so when we repeat a random experiment several times, we call each of them a trial. Okay, these are just keywords that you should keep in mind. Okay. Okay, so let us see some example. Okay, so random experiment could be a twice of a coin. Like I said, sample space in this case are heads or tail. Okay, so we can usually write in short form as h comma t. And random experiment, another random experiment. This is another example where you roll a die. Okay, and sample space, since die is in this case, we assume that it's a six-sided. Okay, so that the sample space in this case are possible outcomes that you can expect. So this will be 1 or 2 or 3 or 5 or 6 facing upwards. Okay, uh, another random experiment could be observe the number of iPhones sold by an Apple store in some Boston, let us say. Okay, so in this case, the sample space it can be like we cannot like the sample space is like all possible outcomes. It could be zero phones sold, it could be one phone sold, it could be three, and it could be like it can keep going because these sales keep happening, right? So we cannot stop here in this case, although it's a countable set, but we don't know where to stop. Okay, but still the sample space captures every all possible outcomes. In this case, it's like the whole numbers, right? Another random experiment could be observe the number of goals in a basketball match. So in this case, again, the sample space could be like there are zero goals, there are one goal, there are two goals. In theory, there can be like many goals, right? Depending on how quickly someone scores. Okay, but in reality, we know that number of goals may not go too far. Okay, it may stop at some point. Okay, now going, so defining this basic thing about some key terms and so on. Let us go back to trace the definition of classical probability, and this is the book or the notes that I was talking about, where Cardano had written. Okay, so this is a 15 page, and it's written in Italian or Latin maybe. Okay, so in chapter 14 of this his notes, Cardano gives what some would consider the first definition of classical probability. Okay, so this is why we believe that he should have been considered the father of probability. And so what he is trying to say here is, this is an English translated variant of his notes, and what he's trying to say here is, so there is one general rule, namely that we should consider the whole circuit. Okay, by whole circuit he means the sample space and the number of those casts which represent in how many ways the favorable result can occur. Okay, so you can think of cast as event. Okay, so how many ways the favorable result can occur, and compare that to the rest of the circuit. Okay, so again, rest of the circuit, and according to that the proportion should should be should the mutual wagers be laid so that one may contend on the equal terms. Okay, so what we can get from here, what he's trying to say is like he's considering sample space, and then he's considering the favorable results. Okay, so this is the favorable results are the event that I'm expecting, right? So for example, if I toss a coin, head and tail are the all possible outcomes. So that forms a sample space, and what I favor is head, let us say, then that becomes an event for me. And then we may talk about the proportion. Okay, or the ratio. Okay, so we need to consider the sample space, and we need to consider the favorable results that we are talking about. Okay, so he had these things in mind, and then comes the Pascal, and Pascal was a French mathematician, and he actually defines it in a more proper way. Okay, so here he is talking about he was known for variety of things. Pascal was a very well-known mathematician. This Pascal triangle we already saw, but he did a lot of work. Okay, so in engineering, like tidal dynamics and so on, so that's more towards towards physics, you can say. And then in mathematics, he has contribution to so many things like Laplace equation, Laplace transform. If you are doing signal processing and so on, you have seen these things. They are so important tools. And then in statistics, obviously, he's considered to be the main guy behind the modern theory of probability. So, and then obviously he also contributed in the Bayesian statistics and so on. In physics, he had contributed to existence of black holes, gravitational collapse, stability of solar system, and so on and so on. Okay, so he was very prolific. But let us focus on the probability. Okay, so this is a snapshot of the I traced the place where he actually defined. Okay, so this is the book that he wrote on probability. You can say that this is the main probability theory book, the first probability theory formally written by Laplace. Okay, in 1812. Okay, so this is a long time ago. Now in the theory, this is a French, and fortunately I can read French. Because I was in France for some time. So what we can find out from his thing is we can go to this line here. Okay, so he is saying is that probability is a measure. Okay, the measure of that probability is the one which is a fraction where the numerator is the number of favorable cases, and where the denominator is the number of total possible cases. Okay, so this is where we trace what is trying to how he defined. Okay, so all the cases. Okay, so this means all the possible cases, and then we have the favorable cases. So this is the event we are talking about, right? So this is the sample space. So this is the sample space, and this is the event. Okay, so from here we can already decode what he is trying to say. Okay, so the probability of an event, the way he is defining, is the number of the so this is like the cardinality of A. Okay, divided by the cardinality of the sample space. Okay, so this is the number, right? This is the number in the set theory terms, all the possible cases, and then the cardinality of the sample space, and then cardinality of the favorable cases we have. Okay, so this is what Pascal concretely writes. Cardano was a little bit vague, but almost there. So this is the translation of the last line, and another thing to note is what he's trying to say say before. Okay, so what he's trying to say here is this line. Okay, so what he's saying, Egelma is like equally possible. Okay, equally possible. Okay, so what he's also emphasizing here is that all events must be equally likely. Okay, so so when you are throwing a coin, then it should be that head and tail are equally likely. Okay, in that case, this is how he defines the measure. Okay, so that's an assumption that he makes. Okay, so let us define the probability space that we let us define the finite probability space, let us say. Okay, so finite probability space, as our intuition suggests, the outcomes, total number of outcomes should be finite, or in other words, in set theory notation. Okay, so this is our sample space. S denotes the sample space for us, and this is like finite. So it's the cardinality of the sample space is less than infinity. That each outcome I, so let us say the outcomes are tagged by by numbers. So let us say the outcome I has probability greater than equal to 0. So probability are always considered to be greater than equal to 0. Okay, so it cannot be like negative. Okay, so either event may not happen, or it will happen with some probability. Okay, so negative doesn't make sense here. Okay, probability sum to 1. Okay, so in an experiment, and assuming that we have considered all possible outcomes, okay, then the probability should sum to 1. Okay, so then the probability should sum to 1. And because we have considered all possible outcome, so the sum should turn out to be 1. If the sum is not turning out to be 1, then you have missed some of the outcomes. Okay. Event, as I described before, is a subset of the set of all possible outcomes, and the probability of the event will be the sum of the outcome probabilities. So in the event A, I may have some outcomes, and then probability of that event will be the sum of these outcomes. Okay. Is pi equal to 0 possible? Okay, so is it possible that some event may not occur? Well, it is, but why would you consider such outcome anyway, right? If the probability is anyway 0, you can exclude those from your sample space anyway. If you are sure that probability of the ith event is 0, then you can always delete that. So a finite sample space with equally likely outcomes. So here we are talking about those cases where we have equally likely outcomes. So any outcome you pick, the probability of that outcome is the same with any other outcome you pick. Okay, so those are called equally likely outcomes. Okay, so in those cases, we can define it here. So this is the sample space S. Let us say, so this is a finite sample space. Okay. So in the finite sample space, we can define the probabilities of the equally likely outcomes. So in this case, according to the definition here, equally likely, what we are saying is the probability of the ith outcome is same as the probability of the jth outcome. That's what equally likely means. And since all the outcomes are equally likely, and the probabilities of these sum to 1, right? So probability of S1 plus probability of S2 plus plus probability of Sn sum to 1. Okay, and then these are all the same. So we can pick any of these, and then we have n times probability of, let us say, Si. This is equal to 1. So this implies probability of I is arbitrary here. So Si is 1 by n. Okay, so we can, given the assumptions that it is finite and it is equally likely outcomes. Okay, equally likely outcome case, then we can immediately say what is the probability of each of these outcome, which is same, and it is equal to 1 over n. Okay, we need to assume here finite sample space. That's how this is okay, right? So if it is countable or and still infinite, then probability of those will be, I mean, we won't be able to define in this way. Okay, we cannot be like, it will be like 0, right, probability, but we will see the other tools. Okay, we are dealing with finite probability space in the beginning. So this is the case. For example, a simplest example of this case is heads or tail. So the sample space in this case is head or tail, head and tail. Okay, so the event could be head. Okay, and so then from this, this is a finite. So the experiment is to toss a coin. The sample space is all possible outcomes, which is head or tail, and the event, or one of my favorite outcome that I'm expecting, is head. Okay, and so this is a finite probability space, equally likely outcome, because either of the head or tail can happen. It is not a skewed experiment in any sense. So in this case, in those cases, since we know that probability of head and probability of tail are same, in those cases there is 1 divided by n. N in this case is 2. Okay, so and we can for any event A with cardinality A equals to m, we can write the probability of the event A to be the cardinality of the event divided by the cardinality of the sample space. Okay, so this is the thing. So now you already have one tool to in the cases when your sample space is finite, your event set is finite, you know now to compute the probability. Okay, and additionally you assume that the outcomes are equally likely. In those cases, you know how to compute this. Okay, So another example is a die, right? So so another example is a die where you have some numbers here, 1, 2, 3, 4, and this is a finite sample space because the sample space is 1, 2, 3, 4, 5, 6. And event could be, let us say, even numbers, so 2, 4, 6. So this is a finite sample space, okay, equally likely because either any of the 1, 6, 4 can appear. In those cases, the probability of A, so in this case, the cardinality of A is 3 and cardinality of the sample space is 6. Okay, so this is the probability of obtaining an even number is 1/2. Okay, so you remember, now you see why we did counting. Okay, because at the end of the day, you have to count. In this case, you don't see how what we studied helped because this was easy. Okay, but we can make a problem. You can make problems where actually you will need a good amount of counting techniques. Okay, to take this ratio. Okay, sometimes even to know what is there in the sample space can require those tools that we studied. Okay, okay. So now let us go ahead and define it formally. Okay, so so far I have shown you the keywords. I have discussed finite probability space. Now I will concretely define. So what is a probability? Probability is nothing but a measure. Okay, so it's a measure. It's a real number. Okay, so it's a real number between 0 and 1. Okay, so it's a measure denoted by PA, or sometimes I will use both these sometimes depending on the context. Okay, so if P notation is used somewhere, then I will use PR and so on. So P of A or PR of A is called probability of A. Okay, this value is between 0 and 1. Okay, and you could have defined some arbitrary value, right? But we will stick to this, right? So between 0 and 1, that's the way we define. Okay, so that shows how likely the event is. If PA is close to 0, it is very unlikely that the event A occurs. Okay, if PA is close to 0, then it just means that, well, so the event almost will not happen. Okay, it's very close to 0. On the other hand, if PA is close to 1, that it means that it is very likely to occur. The main subject of probability theory is to develop tools and techniques to calculate probabilities of different events. Okay, so that's what we are doing, why we are doing this course. After all the classical definition and some intuition behind the probability and how we compute and so on, people came up with some set of axioms. Okay, and this set of axioms are enough to build the whole of the probability theory. Okay, so there are 3 axioms of probability, and it's important that you know this so that you don't violate these while proving results. Okay, so for any event A, so these are axioms. We take it as it is. Okay, we don't prove axioms, right? We prove theorems based on axioms. So we take it for granted that for any event A, probability of an event A is greater than or equal to 0. Probability of the sample space is 1. So that's what we expect. A sample space was a set of all possible outcomes. So if I take everything, then it must be 1. Okay, so probability of the sample space must be 1. And if A1, A2, A3, and so on are disjoint events, okay, so I will discuss this disjoint event. So from set theory point of view, disjoint events just means A1 intersection A2 is empty, or pairwise. Okay, A2 intersection A3 is empty, or A2 intersection A1 is empty, and so on. So these are basically disjoint events. We know that events are nothing but sets, and disjoint event means that as a set they are disjoint. Okay, so if that is the case, then the probability of the union is sum of the probability. For example, in the coin toss example, if we have an event of getting a head, and if we have an event of getting a tail. Okay, so these are like disjoint events. So let us say this is A1 and this is A2. Okay, so we know that A1 intersection A2 is empty, right? So A1 intersection A2 is empty. So this is a disjoint event. So this implies that that the probability will be nothing but the probability of probability of A1 plus probability of A2. Okay, so which will be half half, and this is coming out to be 1 because A1 union A2 is nothing but whole sample space anyway. Okay, so using the axioms of probability, we can prove some of the results. For instance, here for any event A, we have probability of A complement is 1 minus probability of A. Okay, so this can be proved easily because what does it say? Because from so what are the axioms we are we have to prove this using using probability axioms, right? So what can be invoked here, right? So what we know is that the sample space has to be probability A union A complement. Okay, so because A complement will include all the remaining things, so sample space will be A union A complement. We know from the axioms of probability that that probability of the sample space is 1. So this implies probability of A union A complement is 1. And another thing we know is that these are mutually exclusive. A and I mean disjoint. Okay, A and A complement are disjoint. Because A intersection A complement is empty. Okay, so these are disjoint. So for disjoint events, we also know that. So this implies that probability of A union A complement is probability of A plus probability of A complement. Okay, because these were disjoint events. And then from here, so this is equal to 1. So from there, we know that probability A complement will be nothing but 1 minus probability of A. Okay, so that we proved it. The probability of the empty event is 0. Okay, so you can again prove this using axioms of probability. Why probability of an empty event will be 0? You can use the same trick that I used here. Okay, so you can write sample space as sample space union the empty set. Okay, just like this. Okay, we don't put curly braces. So so these are mutually exclusive. Probability of the sample space is 1, so probability of the empty set will be 0. Very easy. Okay, probability of any event A. Okay, that should be like this. So probability of any event A must be less than or equal to 1. Okay, so that you can get it from here. Okay, so you can prove it from here. Prove using this. Okay, so what you are saying here is that probability of A complement plus probability of A is 1, but we know that probability of this is greater than or equal to 0. Okay, so this implies that probability of A is less than equal to 1. We also know that probability of A is greater than or equal to 0. So only possibility for this identity is that probability of A is less than or equal to 1. So that proves this. And if A is a subset of B, then probability of A is less than or equal to probability of B. Okay, again, you can prove this using axioms of probability. Okay, similarly, you can try to prove these two using axioms of probability. Okay, should be simple enough. Coin toss example. Let us compute now let us use some examples. So a coin is another thing I would like to define is fair. Okay, when something is fair, a coin is considered fair if the likelihood of getting heads or tail is the same. Likelihood of getting head or tail, in this case the coin, in the coin case we have the sample space is head or tail, and we call the coin fair if the likelihood of getting head or tail is the same, right? Now calculate the probability of obtaining head when the coin is tossed once. This is an example that I already did. So the sample space in this case is set of all possible outcome head or tail. The number of head possible in one coin toss is 1. Hence the probability of obtaining head is the fraction 1, 2. This is already using the assumptions of finite probability space and equally likely outcomes. We have derived this. Let us see another example. We roll a fair dice. What is the probability of an event this? Okay, so this is again easy, just for quick thing. So this is the sample space. This is a finite probability space. Finite probability space. Okay, we are dealing with finite. Otherwise, the things won't work the way it is, right? Because in finite only you are talking about fraction and so on. Okay, if it is infinite, then sample space cardinality is infinity, right? It doesn't make sense to divide by infinity, right? Okay, so let us see, stick to finite in case. So, and then in this case, the event is 1 6, and then the probability of the event is the cardinality of the event divided by the cardinality of the sample space, which is 2 by 6. Okay, so which is 1 by 3. So that's the answer. Okay, this is a very trivial examples to show. So this is another example where we are saying a coin is tossed. The experiment is a coin toss, and the event that we are defining is obtain at least one head. Okay, when two fair coins are tossed simultaneously. Okay, so now the question is like there are two coins. Okay, so coin 1 and coin 2. Okay, so let us say head and there is tail here. We cannot see the other side, right? So when two fair coins are tossed simultaneously, what is the probability of obtaining at least one head? Okay, so what is the probability of obtaining at least one head? So in this case, when you are solving these problems like this, first of all, we have to see whether it's in a finite probability space. Yes, it is in finite probability space because the outcomes are finite. Okay, so first step usually you do in solving problems is what is the sample space, because you need that. Okay, so what is the possible case since you are tossing two coins, so the outcomes are like paired. Let us say it's like head or tail, so you have to consider now pair of outcome. Okay, and so what are the possibilities you have, okay, in the sample space when you do indeed toss two coins simultaneously. Okay, so what are the possible cases you have? I can have head in the first, tail in the second. Okay, I can have head. Okay, I can have tail head. Okay, and I can have tail. Okay, so these are the possible outcomes that I'm expecting when I'm throwing a coin. I'm throwing two coins simultaneously. This is for the first coin and this is for the second coin. Okay, so now the question is the event, the favorable outcome, the outcome that I am expecting is called an event. Okay, and what is there in this case? So in this case, we are saying obtaining at least one head. Okay, we are not saying which coin should have the head. We are not saying the first one should be head or the second one should be head. We are just saying at least one head. So at least one head cases are like either this way it holds, or either this also I got one head, or I have this. So here also I got one head. Okay, now this is a finite probability space, and any of these possibilities, any of these outcomes are equally likely. Okay, so hence the probability of the event is the cardinality of the set E divided by the cardinality of S. Okay, so the cardinality of the set E is 3 and cardinality of the set S is 4. Okay, so the probability of getting at least one head in when two coins are tossed simultaneously is 3/4. So this is the question. It's slightly different. Again, we are tossing two fair coins and they are tossed simultaneously. Now the question is, what is the probability of getting at least one head? Okay, so what is the okay? I'm sorry. Not two, okay, 10 fair coins. So this is a 10 fair coin case. I was wondering why, how come it was two. So 10 fair coins are tossed simultaneously. The first step is to, so this is the sample space that we have computed. Sample space or the cardinality of the sample space. Okay, so this is where countings come in picture, right? So what are the this is like you are tossing 10 fair coins, and what are the possible outcomes you are expecting, right? So there are like, you can consider these as 10 places, right? Okay, so these are the 10 places. So at each place, what are the possible outcomes you have? It's like either head or tail. Okay, so this is like two possibilities, either head or tail, either head or tail, because it could be repeated. I mean, it can happen that other coin also has either or head or tail, right? So so these are the cases we have. So this is 2 to the 10. Okay, and what is the probability of getting at least one head? Well, in this case, we may try to solve this problem in a different way. Rather than asking at least one head, let us ask a case where we had no head at all, and then we use the negation of that. So let us say the case which has no head at all, and this is the only case with no head at all. Okay, so this is the only case with no head at all, and from our logic theory we know that the negation of this is at least one head. Okay, so getting at least one head. So, and using the probability axioms, right? So this is an event. So event one is let us say no head case, and event two is nothing but a complement of E1 actually. Okay, so a complement of E1 is like at least one head. Okay, so so this is E1 and E1 complement, right? So we have seen in the previous example that probability of E1 union E1 complement is 1, and this is these are like disjoint events. So this is like so the probability of E1, I mean what we want is probability of E2, right? So probability of E2 is 1 minus probability of E1. Okay, so probability E1, if I calculate, which is the no head case, and from there like we can compute. So it's very easy now. So so there was only one case with no head. So we subtracted that from the total cases. The probability of getting event with at least one head is 2 to the 10 minus 1. Okay, and then we divided by total sample space, cardinality of the sample space, and that's how we got answer. Now consider an experiment of throwing two dice. Consider an experiment of throwing two dice. Okay, let us say it's blue and red one. Okay, so we are moving from coin to dice now. So what did we assume here? So in this case, again, since we are throwing two dice, the outcome will be a paired outcome. So it's like first one, let us say, corresponds to the first die, and this is for the second die. And possibilities for x and y are 1 to up to 6. The number of outcomes in this case is 36. Okay, since we are expecting two outcomes and each has 6 possibilities, so this is 36, right? And we assume that all 36 are equally probable. In other words, what we are assuming that dice is fair. Okay, so when we say something is fair, it means that each of the outcome is equally probable. Okay, so that's a keyword here, but this the same thing as saying that the dice is fair. Probability space in this case, or the sample space in this case, is all possible outcome, and cardinality of the sample space is indeed 36 here. In this case, the event will be some favorable outcome that we need to define precisely. Okay, that depends on the experiment that we want to do. Okay, okay. So this is the quiz here now for today's attendance quiz, and you can type this tiny URL out. Okay, so and the time limit for this quiz will be let us say 5 minutes. Okay. So I will start the timer, and then after that it will be 5 minutes. Okay, so try to
send the link on the chat.
You can type out, right? It's not a big deal. You just type out. Okay, I pause the timer right now. Please type out the URL. Okay, and then I will start the timer. Okay, these are very simple quizzes. Okay, first quiz was a little bit tricky, but usually in-class quizzes will be easy. So take participation and okay. So I hope 4 minutes is like 5 minutes is really a lot of time for these easy questions. Okay, so I'm starting the timer now.
So how many questions?
Only 2 questions. Very easy. It is just to check that you are there. Okay. Remember not to click submit. I have checked that last question you have submit button. So you when you submit it will be done. Okay. They will so be careful not to hit submit without answering.
Sir, it's not opening for me, sir.
Those who write answers in the chat, you will get a penalty. Okay, it's a very strict. We have a record of what you are writing. It's even recorded. So if you're writing answers in the chat, then be prepared to get a 0 for the quiz. Okay.
Hello, sir.
Yeah.
It's not opening for me. The URL.
Is it?
Yes, sir. It's not opening for me also.
Okay. Let me check this. Maybe the TA did not set the allow submission thing. It may happen. Okay. So let me check. It is opening. I just checked and it's opening for me. So for me it's opening. I don't see any.
It's
Okay, can you check again? It's opening or not? Okay, let me. Okay.
Yeah, sir. It's open now.
Okay. Do it. Okay. Yeah. Maybe the settings were changed. Okay.
yes,
So
sir.
I will. Okay.
Sir,
Hmm.
I had already submitted before you reset the timer. Responses will
It's
be there,
okay.
right?
Yeah,
Yeah.
timer has nothing to do. Timer has nothing to do with the form. You submitted. It's fine.
Sir,
Yes.
sir, can we leave because like the
Yeah.
second class already start?
Yeah, but it's not yet 10:30. But yeah, if you're done, then you can leave. That's okay.
Thank you.
Yeah.
Excuse me, sir.
Yes.
So, is there any book we will use for the course?
Yeah. So I mentioned in the chat, it's a Sheldon Ross you can use. That's a very standard book, and you can practice from there. There are many worked out examples also. If you need, I can put a list of all the books you may want, but Sheldon Ross is the best one.
Excuse me, sir.
Yes.
Sir, in the Teams app itself, there is a section of quiz too, and there are also questions available, as well as the link which you shared. There also questions are
You
same.
answer on the link, right? I told you about
Because the
going to the link.
responses are not visible in the Teams app, that's why I was confirming once.
Okay. Okay. No, actually both will point to the same, but try to follow the link and then yeah.
Yes, sir, I submitted. Can you just confirm?
What is your name?
Shlok Pandey. SHLOK. Shlok.
Yeah, it's there.
Okay, okay. Thank you, sir.
So, can you also confirm mine,
No, no,
please?
I cannot confirm one by one. There are 200 students. We will see later. Okay, you just submit and that's fine. Today's class is over. We will show you the response either in the class or usually it's better to do this in the tutorial. They will show you the response. Okay.
Hello, sir.
Yeah.
Sir, what would negative probability or probability beyond 1 mean, theoretically speaking?
No, negative probability. Yeah. So as I said, like we agree on the scale of 0 to 1. Okay. And then we always assume that either event happens or doesn't happen. Like negative, how will you interpret, right? The issue is like, how will you interpret something being negative, right? So something either happens, then we will say, okay, it happens with some positive number. Okay. So to answer your question, like it doesn't make sense to define negative probability. Okay. Okay. So the quiz time is over. I can say here, and I hope most of you have submitted the responses by now. I hope so. And if not, then yeah, you will lose these quiz marks. Okay, thanks. Bye. We have to stop the presentation, otherwise it gets stop recording.